All right, let's get right into it. Today, we're going to talk about the thing that makes you, well, you. We're going to break down the fundamental building block of your brain, your entire nervous system, the incredible electric messenger we call the neuron.
Okay, so picture this, right? You're at the doctor's, they give your knee a little tap, and your leg kicks out before you even consciously register it. How in the world does that happen so fast? Well, it all comes down to a super high-speed communication network running through your body, and we're about to meet its star player.
To get how that reflex works, and really how anything works in your brain, from tying your shoes to having a thought, we have to understand the basic rules of the road. It's not just chaos in there, it's a super organized system, and it all boils down to one type of cell and a couple of really key ideas.
And this is the star of the show, the neuron. This is the specialized cell that's zipping all those messages around. You can kind of think of it like a biological wire, but way, way smarter. And see its shape? You've got these branchy-looking parts. Those are the dendrites. They're the inbox. And then this long tail is the axon, the outbox. That basic structure, it's everything.
You know, for the longest time, scientists actually thought the brain was just one big, tangled mess of wires, all physically connected. But then this absolute genius, Santiago Ramon Cajal, came along and figured out, nope, it's actually made of billions of individual separate cells. And that idea, which we call the neuron doctrine, is literally the bedrock of all modern brain science.
And this guy, Cajal, he was on a roll. He also figured out the second big rule, which he called the law of dynamic polarization. Now that sounds complicated, right? But all it really means is that traffic inside a neuron only goes one way. It's a one-way street. No U-turns, no exceptions. The information has a set path it has to follow.
And here's that path, laid out nice and simple. The message comes in the dendrites, the cell body, also called the soma, sort of processes it, and then whoosh, it shoots down the axon to be passed on from the axon terminal. In through the dendrites, out through the axon. Every single time.
Okay, so the message travels down this one-way street inside the neuron. But what happens when it gets to the end? How does it get to the next neuron in line? They aren't actually touching. There's this tiny little gap, and that's where the real magic happens.
This incredible little space is called the synapse. Think of it like a ferry terminal. The electrical signal arrives at the end of the line, and that triggers the release of these tiny chemical messengers. You've probably heard of them. They're called neurotransmitters. They float across the gap like little ferries and dock on the other side, on the next neuron's dendrites. And just like that, the message is delivered.
Right, so these messages aren't all the same. They basically come in two flavors: go and stop. The go signals are called EPSPs, that's for excitatory. They're like a little push on the gas pedal, telling the neuron to get ready to fire. The stop signals are IPSPs, that's inhibitory, and they're like tapping the brakes. Now, here's the thing. Each one of these little signals, these go or stop votes, is just a tiny, tiny little nudge, a small blip in the neuron's electrical charge. One vote on its own does basically nothing. And that's super important, because any given neuron is getting bombarded with thousands of these signals all at once. So this is where it gets really dramatic. Imagine this neuron just sitting there, getting hammered with all these go, stop, go, no, wait, stop signals every millisecond. How in the world does it decide what to do? How does it make a decision? Well, it does a little bit of math, and it does it ridiculously fast.
This process is called synaptic integration. But really, you can just think of the neuron as a tiny calculator. It's constantly adding up all the go signals and subtracting all the stop signals, tallying the votes in real time. And if the goes start to really overpower the stops, well, then things are about to get loud.
And it all comes down to this magic number, -40 millivolts. See, a neuron normally just hangs out, resting, at about -70 millivolts. But if all those go signals add up and manage to push that internal voltage up to this critical tipping point, that -40 millivolt threshold, boom, it fires an action potential. Just look at that spike. It's not a little blip like those other signals. This is a massive all-or-nothing explosion of electrical energy. There is no halfway. The neuron either screams yes at the top of its lungs, or it stays completely silent. And when it screams, that signal goes flying down the axon. Okay, but hold on a second. We keep saying electricity and voltage. How does a squishy little cell, which is basically a bag of salty water and fat, generate electricity? It's not like it has a tiny battery inside. Or does it? Let's dig into the beautiful physics of how this whole electric engine actually works.
So here's the fundamental question.
It's actually all about controlling where certain charged particles, we call them ions, are allowed to be. The neuron creates an electrical charge by creating an imbalance on purpose.
All right, let's look at the key players here. We've got potassium, K+, and sodium, Na+. Just look at the numbers. Inside the cell, it is packed with potassium. Outside the cell, it's swimming in sodium. This separation isn't an accident. The neuron works really hard to maintain this imbalance, and this is the source of its power. So for each of these ions, there's this constant tug-of-war going on. On one side, you have chemistry, the simple rule that things want to spread out from where they're crowded to where they're not. On the other side, you have electricity, positives and negatives attracting or repelling each other. The equilibrium potential is just the sweet spot, the exact voltage where that tug-of-war is a perfect tie for that one specific ion. Okay, so when the neuron is just chilling out, its cell wall is mostly leaky to just one thing, potassium. So what happens? All that potassium that's crowded inside starts to leak out. And since potassium ions are positively charged, as all that positivity leaves, the inside of the cell gets more and more negative. It keeps going until it hits about negative 70 millivolts, and that is its resting potential. So let's put it all together. The neuron gets pushed to that negative 40 millivolt threshold. That's the trigger. Instantly, a bunch of tiny doors, sodium channels, fly open. All that sodium that was locked outside comes flooding in, making the inside of the cell super positive. That's the huge upswing you see in the action potential. Then, just as fast, those sodium doors slam shut and the potassium doors fly open. Now potassium rushes out, bringing the charge right back down. It's this incredibly fast, perfectly timed dance of ions. Okay, I know. We've been deep in the weeds with ions and channels and voltages, so let's pull back. Let's zoom all the way out and see how this one tiny, microscopic electrical event can possibly be responsible for the complex tapestry of our thoughts and feelings. And this is how it all scales up. You've got the single action potential. That's the micro-level event. But when millions or even billions of neurons fire together in sync, they create bigger electrical waves that scientists can actually measure with an EEG. And all that activity requires energy, which means more blood flow. And that's what you see on a big MRI brain scan. But it all starts with that one little spike. So when you boil it all down, we end up right back where Cajal started us over 100 years ago. The bottom line is this: the neuron is the basic building block. Everything your brain does, from that simple knee-jerk reflex to composing a symphony, is just the result of the coordinated electrical activity of these individual cells. So I'll leave you with this to chew on. If every single thing you experience, every memory you have, every emotion you feel, every decision you make, if all of it boils down to this simple on or off electrical signal repeated billions and billions of times a second, what does that really say about the nature of consciousness and what it actually means to be human? Makes you think, right?